Okay, so space propulsion is about putting the payloads from Earth to the space through chemical, and maybe one day with the lasers with the laser propulsion or electromagnetic propulsion. And then those payloads, to move those payloads into space using maybe electric propulsion, chemical propulsion, no propulsion, and then all that types of stuff. The goal is actually to increase the performance, increase the reliability, and then increase efficiency, and also the lifetime, in order to reduce time to launch those things, maybe from months to days, hours, and decrease cost around 2 orders of magnitudes. Well, space propulsion systems are complex systems. In fact, system of systems. Therefore, it involves a lot of processes occurring from atomistic scale up to the mesoscale. So when I say all those goals, that's in the fundamental side of the things. We try to increase those performance and reliability values. Therefore, this program became a platform where many disciplines got involved and conduct collaborative research. Now, there are 3 sub-areas in this portfolio. The first one is a new initiative started a few months ago with a kickoff meeting at NASA Glenn, which is coupled materials and plasma processes far from equilibrium. You heard this several times today. I am going to go a little bit more in detail. They left that job to me, thanks to John and Ali. I have to talk this in detail. And the thing is, what we did, we brought together aerospace, materials, physics, and in fact, interface scientists together to communicate them to each other and hopefully make them to work together. That was the whole purpose. The main goal is to find the atomistic scale response of the material to the plasma and how that response will affect the plasma, if I can explain it in 1 sentence. Okay? Now, the second, and this one is a couple materials and it's a very unique program. Probably at this stage is the only one in the nation. However, I just heard from John Livingston, the Army wants to get involved with this program too, after they listen to you. So we have no value, you have the value. And then she actually should take the credit, she started this. And the second sub-area is the energetic materials, started 3 years ago with NASA partnership. And the focus area in there, it was nanoenergetics. And then if you have been in the other briefings, that we had a lot of successes in that. We had an aluminum ice rocket to be flown. And then we also got encapsulated nano-aluminum in this program. We also got distributed catalyst for monopropellant combustion. We did that too. Now I'm going to show some other things. But in contrast to the first area, the novel energetic materials, everybody does it. Everybody has an energetics program for different reasons. So in order to avoid duplicity and then exchange the notes, and then find the commonality, we created a multi-agency coordination committee for this. We already got together twice, and then hopefully we'll get together sometime this month also. Now, the major goal here is to, by changing the atomistic scale events, how you can affect the mesoscale events. Okay. Now, the third sub-area is nonlinear multiscale multiphysics. Probably you heard that term 150 times this week. High-pressure combustion dynamics. That is looking a new approach for an old problem, which is called combustion instability. Combustion instability, it's about the acoustic field in the chamber coupling with the combustion process. Well, whatever they say about the complex problems, this is the mother of all complex problems. So we want to, I'm going to talk a little bit about it. There are things I like to do, like a physics mining in this program. And there is some approach, which you heard from Dr. Darema on Monday, I believe, about dynamic data-driven applications. Anyway, let's start with the first one. Couple materials, what we have done. Nothing. That's the end of my talk. What's happened? Oh, somebody sabotaged my talk. As I said, we had a kickoff meeting in NASA Glen, but before then we had 5 focus areas in this initiative. The first one, steady-state power low-density plasmas, which is directly related to all electric thrusters, is known today and used in the space, like Hall thrusters, like ion thrusters, like helicon thrusters, and others. I'll talk about it in a little bit detail. The second focus area is pulse power relatively long density plasmas, is related with my reverse field configuration concept, which I talked in detail last year, if you were here. And also related with John Ligonstein's program. In this case, the goal is to find out how the plasma will create excited states. Therefore, the radiation will be very important in this case. And also chemical reactivity is very important in this case. Now, the University of Washington working on this, and John Ligonstein's lab task at the Propulsion working on this. They are doing computational, and also part of my lab task working on this at the Propulsion Directorate right now. Third area is funded by Dr. Sayer, plasma electrode interactions, because of his involvement in the Ukrainian initiative about low work function ceramics. And in this case, they are going to look at the plasma electrode interactions, which is directly related with my program and also John's program. The good example of, in this case, plasma electrode, Princeton, JPL, and also Case Western involved with this focus area. The good example of the high-density thermal plasmas is the plasma generated between rail and armatures at the electromagnetic accelerators. Those plasmas are very high-pressure plasmas, And they will be a radiation flux, as well as a particle flux, as well as the chemical etching on the materials. And then what they are looking for, what is that material threshold, and how they can increase that material threshold. The last one is about particle impact on the satellites. Those particles can be Cassandra's particles, can also be my particles, which is generated from exhaust plumes. What they are looking for in here, at the atomistic level, material response to their particle impact, which can cause charging, which can cause contamination, which can cause the thermal effects, they increase the satellite temperature. In this case, it's actually Penn State, Maryland, and also University of Illinois Materials Department working on this one. And this one, University of Texas, Aerospace, Physics, and Chemistry, and also, University of Illinois working over here, University of Iowa working over here, Rajan here, and Craven is over in the fourth one. Any case, now we end up having 34 principal investigator, 7 grants, and 19 institution program established right now. Just started. Now I'm going to talk about how we got here. This didn't born yesterday. I mean, these problems exist. Now I'm going to give you some examples what we mean by non-equilibrium, or what we mean by multiscale, hopefully. If you take the first one, there are 3 teams on it. One team is funded by Dr. Sayer, which is headed by Nasser Ghanim. What they are going to look for, actually, what is the material relationship with the plasma, but closer to the surface. Okay? This is much more like in the atomistic scale behavior of this problem is. They are looking also the heat transfer in this material, then also how they can remove that heat, which is getting closer to your area, through some material design. Okay? The second group, there's one thing is known in electric thrusters, is the grain attachment. Actually, Ali told you about that this morning, I believe. Those materials, insulators, mostly done by ceramics. Ceramics has particles, and ceramics has grain boundaries. And grain boundaries are known to be the weakest point in the material. And in fact, in electric thruster, erosion starts from the grain boundaries. Those group is going to look for, this is the second scale, for this problem in addition to the sputtering. Third team is actually looking for the bulk plasma. How that bulk plasma affected by, which is mostly is a mesoscale or micron scale events, affected by this close to boundary material response. Now, since we are talking about this multi-scale, multi-things, let's look at what we are talking about, okay? If you look at a plasma, those steady-state plasma, what we have here, actually, for example, secondary electron emission, when an electron hits a material, material can emit electron too. Okay, that's called secondary electron emission. Or sputtering, an ion hits a material, there's an atom can leave the material. All those things happen in atomistic scales, very close to surface. Electron-neutral collisions, which can cause ionization, and maybe it can cause the resistance because of the electron slows down. Electron wall collisions, in addition to the secondary electron emission, can cause absorption, right? And also can cause the heat in the material. Now, if that electron emission beams generated, those can generate the beams. If that beam goes to the sheet boundary, that can, because of the other particles over there, they can pile up. Therefore, the density will increase. Because of the high density, it will cause the sheet instabilities. The same thing happens in the bulk plasma too. Because the electrons comes from the cathode, when they trap in the magnetic field, they create a rotating beams. If that beams can hit some other particles, then they can create the beam drift instabilities. And those things can be coupled too. I will show you some examples of that. The most famous ionization instability is the breathing instabilities. That's the starvation for the atom in an electric thruster. And it's a known thing. Because that ions generated, they leave the thruster right away. They are very fast. But ions are the feeding gas. They're coming with a certain velocity in the system. And at some point, that thruster shuts down. Because that shuts down, starts again, they create breathing instabilities, which actually you can even detect. And based on the frequency of the breathing instabilities, you can even say what kind of thruster is it too. Okay? Anyway, now, if you look at the possible, possible tools for this, for example, in the computational field, usually the things happening in the atomistic scale, you can look at with the quantum mechanics together with the MD calculations. All the chemistry people know this very well. Materials people know this very well. And then, if you are statistical, those are deterministic tools. If you look at the statistical, you can use the Monte Carlo collisions or the Boltzmann equation. And the more popular is the particle in cell codes, which they use in several places. When there is a large amount of particle collisions, which can cause the increased excited states in those atoms, then you can actually radiate from those atoms. That radiation, if you need to look at that radiation, that's what the Jean-Luc Cambier are doing at the Propulsion Directorate, collisional radiative kinetics you need. But if you have very high pressures, very high densities, then you can always use magnetohydrodynamic, which is the good old Navier-Stokes with the Maxwell equations. Those are tools available. There is also a lot of diagnostic techniques available, which you have heard from Lee, from everybody, is what they use, the Theta-Hertz interferometer. Now they can do it in a much more smaller place where measuring the electron densities. And then you can use Raman scattering together to look at the densities of the atoms, this, that. Now, if you look at material side, you have also similar scales. They have the electronic structures, and then it can go to the dislocation dynamics, and all the other things. And then we learned in the workshop, I learned actually, the others they knew. I'm the last learner of everything, as at home too. The people who are doing the modeling over here, actually they really cannot connect to in the micron level or mesoscale behavior. So maybe now one can appreciate how complex the problem is. There are two different disciplines, let's say, physics and the materials. They both have a lot of unknowns in it. Okay, for an example from the history, let's look at the secondary electron emission. You know, when the Hall thrusters, that was a technological surprise in 1990s. When we discovered that Russians, they are using Hall thrusters all over. So suddenly there was a quick interest here. And at the same time, the interest for the small macro satellites came out. So they said, let's reduce the size of the Hall thrusters and use on it. Well, when they reduced that Hall thruster to less than a kilowatt level, the efficiency went down to 10%, 15%. Then they say, oh, what's going on in these thrusters? Then we started working on it at MIT, and then looking at some modeling of this thruster. When they use that, they use the ions, everything as a particle, but they use the electrons as a fluid. That means that electrons are in equilibrium. Let's look at what I mean by secondary electron emission. Any plasma, which is a neutral plasma in my case, and gets close to a wall, you immediately create a sheet, and it create a sheet potential. Even though potential over here is 0, it will be around minus 30, 40 EVs on the wall. What that does, if it sees ions over here, that ions, when it sees that's, aha, I'm going to go and hit this wall, and it does. And that causes the sputtering and all kind of the erosion. But electrons also, at the highly energetic electrons, will pass over this wall and then go and hit it and cause a secondary electron emission if the material is secondary electron emission producing material, such as boron nitride, for example. Okay? Now, what it happens, if we are using, this is Maxwellian, is the equilibrium case, in that case, those highly energetic electrons leaving from here, that electron velocity distribution function has enough time to create that energetic electrons. And what it does, those created keeps going, right? Eventually that sheet will collapse because of the secondary electron emission. Now, what's going to happen, all these higher energetic electrons? They are going to hit the wall. So, in terms of heating the wall, this is bad. That's what the conclusion is. If it is for the erosion of the wall, it's good because ions cannot hit anymore because there's no negativity over there. Only one problem, though. This experiment says something else. Experiment says that actually when we give the discharge voltage, maximum electron temperature is going to increase. And then after a certain level, it is going to create a plateau. Okay. Now, why? Because the plasma mean free fat in thrusters are too high to achieve equilibrium. Non-equilibrium, right? Now, you can, then after this, we did this, in fact, that Mike 5, who did that, went to the lab, propulsion lab, and created the colosseum, which has been used for several things in the Hall thrusters. Then it became the HP Hall code. Now they are still using that code. After that, in Stanford, they used the Boltzmann equation to find out the non-equilibrium effect, but they cannot do anisotropic one. They can only do the isotropic one. You know, most of the densities around here, if you see that, well, wall potential does not even change. You see, you can get two completely different answers with two completely different models. So one has to be very careful what kind of tools they are using. In this case, it didn't change. So the conclusion of this sheet does not collapse. So secondary electron emission has little effect on erosion. Well, afterwards, in Princeton, they did a particle in cell simulation of this. Then they can find out they are not only non-equilibrium, they are also anisotropic. Okay, the directions is important over here. They perfectly could generate the experimental result. And this peaks over here, that's what I was talking about, the secondary electron beams, which is generated in those plasmas, which can cause the sheet instabilities. Okay? Now, with this information, so SE is not important, so it shouldn't be. Then they say, what is the most strongest material we can use, right? The most strongest is the diamond. So let's make a Hall thruster from diamond. Well, of course, it's going to resist all kind of erosion possible, sputtering, this, that, because there's not many free electrons in diamonds. But what had happened, when they used that, the thruster efficiency went down, a lot of instabilities occurred in the thruster. So strongest is not better in this case. Then later on is the same element, but in a different thing, the carbon velvet wall, which has been used other places too. When they used that, SEE, secondary electron emission, completely disappeared. In fact, most of the plasma sheet instabilities disappeared, which is obviously they are related to. They also attenuated some of the breathing oscillations. So there's a coupling over there we don't know. Okay? So in the same way, it is same element, different structure, architecture, you can get the different result. That's what Ahmed Ghanim's group in these things, they are looking, not only looking for the material itself, they are looking for architecture of the surface. That's a very important thing. Okay. Oh, 12 minutes I have that? Oh my God, so I have to be fast. Okay. As long as the novel energetic materials concerned, in addition to the molecular synthesis of the energetics, the nanoenergetics opened a new door to synthesize and in fact fabricate energetics at nanoscales, which can affect the mesoscale behavior. Now, what is important in energetics? Performance is important, sensitivity is important, right? And then also controllability is important, and also toxicity is important too, can kill you too. Well, as long as performance concerned, now there's some difference exists. As long as the propellants concerned, we like to have a high energy release and also low molecular weight products in order to have a high specific impulse and thrust. We do not like detonations, and we like to control the energy release. However, if you are working in an explosive area, one would like to have a very rapid rise of the pressure, which is called brisance, I believe, is a French word. And then they like to have a very high detonation velocities. Also, in some cases, they like to have a very high molecular weight products. Okay? Now, that means that in terms of the propellants, intermetallics or termites may not be the main ingredient because those are produce very high molecular weight stuff. But they can be used as additives in order to control or tailor the ignition, sensitivity, and other stuff. We like hydrogen a lot in the propellant business. Why? Because they gives the highest heating rate with the minimum molecular, molecular weight of the products. But hydrogen is very hard to store. You have to cool it down, maybe minus 400 degrees Celsius or something. However, the scientists start looking for the solid form of the hydrogen. Can we get it? Well, there are some people working on that. The real solid hydrogen, you can, I mean, is closer to the science fiction, but maybe happen one day, I don't know. But there are things exist like metal hydrides or ammonium borane. They can contain the hydrogen. In fact, there are studies that hydrogen can be contained in carbon nanotubes or the graphene sheets as a sandwich case. Now, metal hydrides, beryllium hydride is the best one, but it will kill you, right? And but on aluminum hydride, another one is a good one. And the lithium hydride, we work on it at the University of Rome with Dr. Bruno. Any case, 8 minutes, okay. Now, let me show you some examples what happened over here. One of them is pretty much showing that how new tools can change things. Ammonium perchlorate has been studied for many decades, and then it's been known that they have a slower burning rates. So what they do when they are burning, if you're burning in a composite propellant, it will stick out. And it will burn in something like an inverted cone-shaped diffusion flame. Because the ammonium borane is the oxidizer rich, and that around is the fuel rich. And that's what has been used in the state-of-the-art models today. But when they did that experiment with the higher atmosphere, with the new available tools, because of the advancement in the lasers, practically, they realized that actually, when you increase the pressure, ammonium perchlorate burns much, much faster. In fact, it disappears from the surface. In fact, that diffusion flame becomes a lifted, inverted type of flame, which has to be put in the simulation available for this stuff. Now, the second one is about how the nanoscale future can affect the mesoscale behavior. Aluminum used in the propellants for the high energy content and also the instability suppression thing. But they ignite at very high temperatures, around 2,000 degrees Celsius. Because of that, they create the incomplete combustion. They stick together, they agglomerate, and they create a slag and all kinds of problems in the solid rocket motors. But if you can mix that aluminum with the polycarbon monofluoride, then you will reduce that ignition temperature to around 650 degrees Celsius. But if you do a mechanical activation, okay, if you can induce some lattice defects to this, that lattice defects, again, is a material problem. Lattice defects stores the energy. And they were surprised to find out that energy actually increases the heat value, doubles it up. Then you can reduce the ignition temperature around 350 degrees Celsius. Now, the third example is about connecting the atomistic scale modeling to a mesoscale modeling. In Penn State, they added the ammonium borane to a hybrid fuel, paraffin, and that laboratory scale hybrid motor specific impulse increased 10% with a 20% mass addition. But this is micron-sized particles. But what will happen when they increase more than 20%, then there is a crust on the grain and stop the regression rate of the grain. So they decided to find out there's a kinetics is not known. So how they can do that? This is one modeling technique called reactive force field. I think John talked about it a little bit. This is something, when it's too hard to do quantum mechanics, there's something between the quantum and the molecular dynamics. In that field, you just find bond forming and the bond breaking energies as a function of the atomic distances. When the molecules get closer, then they form something. When they do that, it's much faster than the quantum mechanics, and when doing that in the Penn state. Okay? In that calculations, in addition to the density theory, and also finally the Arrhenius kinetics, which we can, okay, I'm getting there, which we can get it. There are two hydrogen elimination reactions, but look at the activation energies for two hydrogen eliminations, and then the oxidation. But there is a polymerization possibility which has a much lower activation energy. So if there is no oxygen or low heating rate, or if in case we can use a smaller particles, they can heat faster and finish that business of the ammonium borane burning without creating a crust. Okay. Third area, nonlinear multiscale multiphysics stuff. Now, we have been working on this topic also many decades. In the recent years, we had a lot of advancement using the, the large eddy simulation together with the subgrid models, and those subgrid models are getting better and better, and then we can, in fact, she didn't let me put that one. It's a 7-injector simulation we have. So we can do 7 injectors in a combustion chamber. Well, those are very complicated problems because we have a coupling of the acoustic field with turbulence, atomization, two-phase flows, whatever you can imagine, and the combustion too. So now there are two problems here. You can get, this happens in every CFD field. Yeah, they're getting a lot of solutions, and when I ask them why is that happening, they say, we don't know. What they say, okay, we do the numerical experiments. It's a fancy word for the trial and error. Okay? Now, what I like to do here, one thing, is to find a kind of physics mining in this CFD codes. I asked that at the large workshop we had in London and also in August. And people, they are thinking about it, getting very hard to write a proposal on it because they are trying to find out too. That's what I need Fariba for this part of the program. The second of this, you got this CFD simulation or the combustion simulation, you have to validate it. Yeah, we are having a lot of advancement in the diagnostics, but we are still not there at looking at the maybe 250 injector in a dense and dirty environment. That's a very hard thing to do. So that comes out something like Dr. Darema talked about on Monday, but in a little bit a simplified version. That's something I had. What we are trying to do, take this whole injector phase, right, and take a slice and define it as an experimental domain. And the rest of this injector phase, we are defining as a computational domain. So from the experimental part, we are getting the pressure oscillations, sending to a controller, and then you are creating what that part should respond to that, and then we are giving back to the experiments. Now, wave structure, we tried to do the Galerkin techniques, didn't work out, and we took the characteristic techniques, and let me show you how those things works. Can you push that one too? The others we don't. You see, in this case, if it's a little bit mean flow in the system, this one becomes extremely unstable. Can you guys push this one? Okay. Now, this one, if there is no mean flow, any traveling spinning wave will become standing wave. Standing waves are not dangerous. Spinning waves are very dangerous. I am trying to say, actually, with a little bit perturbation in somewhere can cause a complete instability and then destroy your engine. Anyway, with this, I am actually, time-wise, I am done. So summary is that we'll get together and try to solve these problems. Okay, thank you.
We have time for a question or two, or comments. Okay.
Yes.
Do you have any explicit plans for bringing this into practicality? In other words, construction of some specific engines that will be making use of what you've developed here? Or in other words, your transition, where this is actually feeding into the design of new engines?
Well, many things we have done, it is getting transitions, actually. For example, 200-watt Hall thruster. We did it based on this MIT work. This work went on the TechSet 2, I believe. TechSet 2 satellite. It is harder to do things in the chemical propulsion side. But we did something, for example, a work, I don't know how much you are involved with the liquid rockets. There are waffles in it. Try to get rid of the instabilities. Then what they find out in my program, all that thing, it was extremely high weight. You can put a little bit stick in it, and it will stop the instabilities. Those type of things, it goes, it transitions to the lab. But my job is, I do not want to restrict myself that something has to go to the practical side right away. Because that's not what we are for. We have lab programs, they are always picking up whatever it needs to be picked up.
Well, I don't disagree with that, yet at the same time, the purpose of your program is to see that we get better engines with all of those things.
That's the ultimate thing.
Yeah.
Yeah, it's ultimate goal is that. I mean, it's, oops, going over you. It is, of course, it's gonna be, has to happen one day. But I cannot say 2 months or 2 years or 20 years. And he doesn't let me anyway.
Let's thank our speaker again.